Grade 11s, what I want you to do is we're going to start with something called quantitative chemistry. So basically what we're doing here is chemical calculations. So up until this point, everything you know about chemistry has been from a theory perspective. But what we're going to do now is, instead of working on the theory, we're going to do actual calculations. So quite a bit of math involved in this section. The date I'd like you to go into your chemistry books, find a new page, brand new page at the beginning of the book, quantitative chemistry. You can put the 19th of April 2022 as your date. And the key concepts we're going to be looking at is atomic mass in the mole. This is a new concept, but I will explain everything as we go. Then we're going to look at composition, the amount of substance, and then something completely new is called stoichiometry. So stoichiometric calculations, that's just chemical calculations related to quantitative chemistry. So the first thing we're going to look at is atomic mass in the mole. Now, an equation for a chemical reaction can provide us with lots of useful information. So let's say I had, for example, iron plus sulfur, and that gives me iron sulfide. So I've got iron here, and I've got sulfur, and I've got iron sulfide. Just going to leave a little space there so we can just have a look here. So we know from grade 10 how to name these compounds. So I know that sulfur has a charge of S2 minus, right? And because it's bonding with this iron over here, and the iron doesn't have any subscripts, it means that the iron we're working with is Fe2 plus. And that should give me FeS. So basically, I've got iron 2 sulfide. So you need to know how to name compounds. If you're struggling with naming compounds, you need to go back to your grade 10 work and go over that section. So what I've got here is I've got a metal plus a non-metal, and that's going to give me an ionic compound. So these are words that should be quite familiar to you. So in this equation, I then have the information I've got here is I've got a reactant, and I've got another reactant, and that reactant gives me my product. So just from one chemical equation, I can find out reactants, products, metals, non-metals, cations. So remember, your metals are going to make cations, and your non-metals are going to make anions. Cations are always positive, anions are always negative. We know of cations is that they lose electrons, and of anions we know they gain electrons. Now everything that you see in this video or in these slides must be in your books. This is a self-study topic, self-study with guidance. I'm here to guide you through it. If you miss out any of these notes and later on we have to come back to it, that is something that is going to be your responsibility at the end of the day. So everything that you see in this video must be in your books. You can use colors, highlighters, it's up to you. So in this reaction, every atom of iron will react with a single atom of sulfur. So if I have a look at that, so I'm just going to rewrite it here. I'm going to say F plus S is going to give me FeS. Okay. So what I'm saying here is that I need one atom of iron must react with one atom of sulfur. And when I have that kind of ratio, it will form one compound of iron 2 sulfide. Okay. However, what the equation doesn't tell us is the quantity or the amount of each substance that is involved. You may, for example, be given a small sample of iron for the reaction. So how will you know how many atoms of iron there are in the sample? So when I'm looking at this, I need you guys to understand something. When I'm looking at an atom, I'm looking at a nucleus, and that nucleus is surrounded by electrons, and inside my nucleus I have protons and neutrons, whatever the case is. This here is one single atom. Now if I had let's say this is a single atom of iron. Okay. Now if I wanted a sample of iron, let's say for example in grams. Now grams I can see. One single atom is, you can't see it with an eye, right? So it's unseen. But when I put many atoms together, okay, I can get a sample. If I get the sample, I can get that sample in grams. If I have a gram of iron, 1 gram of iron, I need to know that in 1 gram of iron, how many atoms are there? If I had 1 gram of sulfur, how many atoms of sulfur do I have? So in this reaction here, I know I need iron and I need sulfur to make iron sulfide. But what I don't know is how much. Okay, so what I want you guys to think about is recipes, right? So recipes is a good example of how chemistry kind of works. It's not some random thing of 1 atom plus 1 atom is going to give me 1 compound. This whole reaction, if I just use an atom and I got 1 compound, this atom I would be unseen. I wouldn't be able to find a microscope that's strong enough or more that's powerful enough that can actually see that. So what we do is we don't work in atoms, we work in samples. And that sample that we work with is usually in grams. And the SI unit we're going to use for grams is G. All right, so what I want to think of is if I have a recipe for, let's say I want to make a chocolate cake. Okay. Now in this chocolate cake, it says I need 4 cups of flour. Now just because I need 4 cups of flour doesn't mean I need 4 cups of sugar. I want you to imagine this now. I don't need 4 cups of cocoa. I don't need 4 eggs necessarily. I don't need 4 cups of vanilla essence. And I don't need 4 cups of baking powder. Now if I look at that, I'm using 4 cups each time, but I'm not going to get a chocolate cake. I'm going to get an explosion inside of my oven. I can't have something like that. So what I need to do is, let's say we start with 4 cups of sugar, of flour, right? This doesn't have to be in your books. This is just a concept that I need you to understand. For every 4 cups of flour, I only need 2 cups of sugar. I only need 2 cups, oops, that's spelling, of cocoa. I might only need 3 eggs. I might need 1 teaspoon of vanilla essence. Oops, the spelling, sorry. And I might only need a half a teaspoon of baking powder. Now, in order for me to use up that 4 cups of flour, I only need 2 cups of sugar. To use up the 4 cups of flour, I only need 2 cups of cocoa, and so on. So chemistry works in the same way. By writing down a reaction like F is equal to S, F plus S is equal to FES, that gives me something on an atomic level, but I can't see that. So in this section, what we're going to look at is, if I was given a sample, let's say I was given 50 grams of iron, how many grams of sulfur will I need? And how much of iron sulfide am I going to produce? So these are all very important questions, the how much, especially when the reaction is in industries. And when we talk about industries, we're talking about kilograms and kilograms of these samples. So in these industrial processes, it's important to know the quantities of your reactants that are needed and the quantity of product that will be formed. If I have a business, for example, and I'm making iron sulfide in the mass production, I need to make enough for my suppliers. If I make too much, I'm in trouble. So I need to know exactly, if I use 50 grams of iron, how much of sulfur am I going to need? How much of iron sulfide? So what we're going to look at in this chapter, we're going to look at how to quantify. So the purpose of this section is how to quantify the changes that take place in chemical reactions. Okay, that's what we want to know. And when we talk about quantify, we're talking numbers. How do we put numbers? So up until this point, you know very well how to name a compound. If I said to you ammonium chloride, simple, NH4 plus and Cl minus, and that's going to give me NH4 plus Cl. Nice and basic. In order to make this compound, you know that I need N2 plus H2 plus Cl2. And that's how I'm going to get there. So you know this. This is what we call a theory. Right? You know the theory of how to form ammonium chloride. The problem is now we want to know how much of reactants will give me how much of product. That's the goal here. So we are looking at quantifying chemistry. That's why it's called quantitative chemistry. And what we're looking at here is the mole. Now, sometimes it's important to know how many particles are in a sample of any kind of substance. Okay. So what you have, or what we understand, is that when I'm talking about particles, okay, I can either be talking about atoms, or I can be talking about molecules, or I can be talking about compounds. Okay, that's what we mean by particles. If I'm talking about subatomic particles, then I'm talking about protons, neutrons, and electrons. Okay, so we need to make sure we differentiate between these things. So when we're talking about particles, we are talking about at an atomic level, at a molecular level, something that is unseeable. So if I have a sample of something, and I mentioned this before, that sample is usually in grams, and we use the letter G. Now, if I'm talking about grams, it means that in these grams here, there are either atoms, molecules, or compounds. Oops. Okay. And what we want to know is, if I have a sample, how many particles exist in a sample? That's what we want to know. So this mole over here, this is the animal, the mole. We're not looking at the animal. We are looking at the amount of substance. So when we talk about the amount of substance, we talk about the mole. So we say, like all units, a mole has to be defined or else based on something that's reproducible. So when I'm looking at a basic definition, I can say a mole, or the mole, is the amount of substance. It's a little bit more complex than that, but we're going to get into that now. So when I'm looking at the mole, I'm looking at the amount of substance. So for the mole, the symbol we'll be using is going to be a small n, and the SI unit we'll be using is going to be MOL with a full stop. If you forget the full stop, it means you don't have the unit. So please make sure you understand that. So the mole is a counting unit. So it's a counting unit. Just like how you count hours or days or so. So we can easily count 1 second or 1 minute or 1 hour. Now, if we want bigger units of time, we look at days, months, and years. And even longer periods of time, I can look at centuries or millennia, whatever the case is. Now, the mole is bigger than a century, bigger than a millennia. It is a very large number. So I can basically say that the mole is the unit representing the amount of atoms, ions, or molecules. Okay, now in this one, if I had to have, remember I said it's a very large number. So we say that 1 mole is equal to 602, 204, 500, and then we've got a huge number of zeros that follow that number. And you've got to know this number, but obviously we're going to simplify it. So in 1 mole of any substance, there is that amount of particles. Now, that number is bigger than a century, bigger than a millennia. So what we do is put it in scientific notation, and we say that 1 mole is equal to 6.022 times 10 to the power of 23 particles. So if I had 1 mole of any kind of substance, I would have 6.022 times 10 to the power of 23 particles. What we call this is we call this Avogadro's number. And the symbol we use for it is Na. Right? So I want you to imagine just how insanely large this number is. If I had this number, 6.022 times 10 to the power of 23 Coke cans, then I would be able to cover the surface of the earth 300 kilometers in deep. Right? If you could count the atoms at a rate of 10 million per second, then it would take you 2 billion years to count the atoms in 1 mole. That is how big this number is. So what we use is Avogadro's number. And this number, it helps us to do the thing I said we want to do. It helps us to quantify chemical reactions. Please highlight this. So in the original hypothesis that was proposed by, his name was, so it comes from, the scientist involved here is Amedeo Avogadro. Right? He says that equal volumes of gas at the same temperature and pressure contains the same amount of molecules. Now, his idea was not accepted by the scientific community, and it was only 4 years after he died that they actually accepted his theory, and it became Avogadro's law. So in order to honor his contribution to the science, the number of particles in 1 mole is called Avogadro's number. Now we use Avogadro's number and the mole in chemistry to help us quantify what happens in chemical reactions. The mole is a very specific number. So if we measure, and this is important, 12.0 grams of carbon, okay, we will therefore have 1 mole or 6.022 times 10 to the power of 23 carbon atoms. Now this is our link, right? Our link between the mole and atomic mass. So if I had, for example, 63.5 grams of copper, and you can pause the video now and go and have a look at your periodic table. If I had 63.5 grams of copper, I would have 1 mole of copper. Or I would have 6.022 times 10 to the power of 23 copper atoms. Right? In fact, if we measure the relative atomic mass of any element on the periodic table, we will have 1 mole of that element. So that's an important thing to write down. So if we measure, I'll write it down for you, the relative atomic mass, remember this, relative atomic mass, and don't forget isotopes. So you need to go and have a look at how we got isotopes last year. If you measure the relative atomic mass in AMU, or we can use the symbol mu, of any element on the periodic table, we would have 1 mole of that element. So this is how relative atomic mass links to the concept of the mole. So when we write down our official definition of what is a mole, you would write something like this. I'll explain further. Please make sure this is in your books. Make sure all of this stuff is in your books. It's important. A mole is defined as the amount of substance that contains exactly 6.022 times 10 to the power of 23 elementary entities of the given substance. Elementary entities means particles. A mole of a substance is referred to as the mass of a substance containing the same number of fundamental units as their atoms in exactly 12 grams of carbon-12. So I'm just going to fix some stuff. You can continue writing down. So we're going to use 3 decimal places here. And don't forget, it's times 10 to the power of 23. And here, you would write it as carbon 12, like that. Please just fix that kind of an error. So what we're saying is that if I had 1 mole of carbon, okay, that means I had 6.022 times 10 to the power of 23 atoms of carbon. Then I would have, a mass of 12 grams. That's how large my sample would be. So for example, I could say 1 mole of helium is equal to 4 grams. And 1 mole of, lithium would give me 7 grams. Right? So when I'm looking at this mass of a substance containing the same number of fundamental units, so elementary entities, you can make a note for yourself, are what we call atoms, you can say particles, molecules, so on. Right. So if, for example, I furthered my examples, and please get these examples into your books. 1 mole of sodium contains 6.02 times 10 to the power of 23 atoms of sodium. 1 mole of hydrogen contains 6.02 times 10 to the power of 23 molecules of hydrogen. And 1 mole of sodium chloride contains 6.02 times 10 to the power of 23 formula units of sodium chloride. Which means that, have a look at the words I'm using. If it's a single atom, atoms. If it's 2, it's a molecule of hydrogen. And then there's formula units. That doesn't mean that when I'm looking at these situations, especially if I'm looking at a compound. In a compound, we add up the relative atomic masses. So if I had, for example, 1 mole of water, okay, which is H2O, I can say that I have 2 times 1 gram of hydrogen and 1 times 16 grams of oxygen, and that should give me 18 grams. So That's another thing. You just have to make sure that you understand how this whole thing works. If I'm looking at hydrogen, hydrogen has an atomic mass of 1 and is 1/12 of the mass of carbon. So 1 carbon has the same mass as 12 hydrogen atoms. They're all related. That's why they use in the definition, it's important that we mention that 1 mole of a substance is referred to the mass of a substance containing the same number of fundamental units as there are atoms in exactly 12 grams of carbon. I'll show you exactly what I just said now. If I look at hydrogen, hydrogen has a mass of 1 gram. In relation to carbon, there is 1/12 of carbon's mass. Okay? Link. That's saying that 1 carbon atom has the same mass as 12 hydrogen atoms. So when we work with the mole, we bring it back to carbon. I want you to think of the mole like this. If I had to say I have a dozen, I would have 12. If I had to say I have a pair, I would have 2. If I had to say I have a couple, I would have 2. See, these words relate to these numbers. If I had to say I had a mole, then I would say I have 6.022 times 10 to the power of 23. It is a word that represents a certain, a specific amount of atoms, particles, or molecules. The next concept we're looking at is molar mass. So the molar mass, and the symbol we use is capital letter M, right, is the mass of 1 mole of a chemical substance. Okay, so our symbol, I said to you now, was capital letter M. So this. And our SI unit is grams per mole. So how we write that down is grams, like meters per second. It's G dot MOL to the power of -1. That is the SI unit, just like meters per second. So you will remember that when I said that if I have mass in grams of an element is equal to the relative atomic mass, if the sample contains one of those elements, then that's the molar mass of that element. You might see in another textbook or in textbooks, they use MM, right, as well. All right, so if I'm looking here, if I'm looking at the periodic table, so let's just break it down quickly of how this looks. So when we're looking at the relative atomic mass on the periodic table, it can be interpreted as follows. The mass in grams of a single average atom of an element relative to the mass of an atom of carbon. It can also be said that the relative atomic mass is the average atomic mass of all isotopes of that element. That's the definition you got in grade 10. Or we can now say that the mass of 1 mole of that element, and we look at molar mass. So when I'm talking about molar mass, I'm looking at, and I'm just going to write it here. If I look here at this table. So if I'm looking at a table like this, you should please make sure you get these definitions, this whole thing. It's all about relative atomic mass. Please get this into your books. You'll have to pause the video multiple times to take down notes, right? All right, so if I'm looking at this table here, and let's say I brought up magnesium, right? So I'm showing you the link between the molar mass, and relative atomic mass. So if I had to look at magnesium and I went onto the periodic table, I would see the relative atomic mass at about 24.3. But that means its molar mass is also 24.3 because it's a single atom. And that the mass of 1 mole of magnesium is also 24.3. It's the same thing, right? If I had to look at another one, so these are your examples. Let's say I had to look at oxygen. If I go into the periodic table, it's going to be 16, right? If I go, its molar mass will also be 16. That's its so molar mass, another word for molar mass is molecular mass. The reason I'm not using molecular mass is because that sounds like the mass of a molecule, but that's what molar mass is. And the mass of one mole of oxygen is 16. If I had to look at something like a transition metal like iron, I'd find that the relative atomic mass is 56. Its molar mass is also 56, except its relative atomic mass is 56 AMU or 56 mu. Its molar mass is 56 grams per mole. And the mass of 1 mole of iron is 56 grams. So that is how we look at relative atomic mass and how it relates to molar mass, how it relates to the idea of the mole. Now there's a very specific equation we use. We say that the number of moles, right, is equal to the mass of the sample divided by the molar mass. Okay, that's the formula. So now we can use symbols. The symbol for number of moles is N, is equal to the mass. The symbol for mass is little m over big M. Your little n over here is measured in moles. That's the SI unit. Mass will always be in grams, and molar mass will always be in grams per mole. This is the formula that you need. It's an equation to calculate mass, moles, and we can even use it to calculate molar mass. Now, I showed you the molar mass of atoms. If we have a look here, if I want a molar mass of a compound, okay, a molar mass of a compound works a little bit differently. So if I had NaCl, for example, then I would say sodium's mass is equal to 23 AMU, and chlorine's mass is equal to 35.5 AMU. So what we do is we say molar mass of NaCl, look at my subscripting please, is equal to 23 plus 35.5. So the molar mass of NaCl is equal to 58.5 grams per mole. 58.50 grams per mole. So that is how you do molar mass of a compound. Molar mass of an atom, like I said, if I had molar mass of an atom, then I would just check the periodic table. So for example, if I had nitrogen, then the molar mass of nitrogen is equal to 14 grams per mole. You cannot write it as 14 AMU because 14 AMU is the relative atomic mass. And if they ask you for the molar mass of an atom, you have to write your final answer in grams per mole. You can do it for any kind of compound. If I show you another compound, let's say we have CaCO3. So I can say, molar mass of CaCO3, I subscript calcium, which is 40, plus carbon, which is 12, plus oxygen, which is 16 times 3. So you just put all of that into your calculator, and the molar mass of CaCO3 is equal to 100.00 grams per mole. And that's how you work out molar mass of a compound. Alright, so back to this formula. Now, in this formula, our base formula, this is the one you get for marks. Okay, but because of the triangle and there's 3 variables, we can do a triangle like this, and it means in step 2 you can manipulate n little m big M, which means if I wanted the mass, I could say n times m. If I wanted the N, the moles, I could say little m over big M. And if I wanted molar mass and I didn't have the compound's molar mass, if I didn't have, so this is one method for molar mass. If I didn't have that, I could just say little m over N. So these formulas, for this one, you get no marks. And for this one, you get no marks. The only one you get marks for is N is equal to M over M. And that is your formula. So, for example, what they could give you, they could say, calculate the number of moles of copper in a sample that has a mass of 127 grams. So what they want here is number of moles. What they've given you here is copper, which you don't know, the molar mass. And you've got the little mass, they've given that to you at 127 grams. So remember, same setup as kinematics. We write down our info, find what we don't have. Now, molar mass of copper, you go find that. Please note, and I'll give you the note for it now. Copper is 63.5 grams per mole. So I want you to just notice here, chlorine and copper. Chlorine is always going to be 35.5. Copper is always going to be 63.5. This 0.5 is important. All other atoms, this is important, highlighted or something. If you use the wrong thing, you're going to get the wrong answer. All other atoms are whole numbers. And I want you to go check your periodic tables. Go and check the periodic table without the names on it. That periodic table will show you very clearly that we take chlorine and copper with their 0.5s, and all the other atoms should be whole numbers. So the first thing you do is you write down your info. That's step 1. Step 2, you need a formula. The formula is N is equal to little m over big M. Then N is equal to 127 divided by 63.5, and N is equal to 2 moles. And I would say you can leave these ones as a whole number. So therefore, there are 2 moles of copper in this sample. Get used to doing that. When you get to grade 12, it gets a little bit more complex. All right, so that's example number 1. If I give you a second example, how many grams are there in 88.10 moles of magnesium? Okay, again, here they want mass in grams. You don't know that. They're giving you the number of moles as 88.10 moles. And they're giving you the atom, which is magnesium. So you need to go find the molar mass of magnesium. So you just go onto your periodic table, you look at magnesium, and you've got 24 grams per mole. So you'll go, that's your step 1, info. Step 2, formula. N is equal to M over M. Now remember I said you get a mark there. Then you can manipulate it. You want mass. So technically M is equal to NM. Your number of moles is 88.10 and your molar mass is 24. And your mass of the sample is 2,114.40 grams. Alternatively, you don't have to manipulate, you don't have to do the second step. You can go N is equal to M over M, and you'll have, don't forget that's mg. We put that in. You can say, 88.10 is equal to little m over 24. And that gives you M is equal to 2114.40 grams. You don't have to do the second step. If you feel more comfortable doing this step over here, you're more than welcome to, but no marks will be awarded. So remember, base formula, substitution, substitution, answer. All right, and that's your second example. All right, there's a second equation. So there's multiple equations for number of moles. So the second equation we look for is number of moles is equal to the number of particles over Avogadro's number. Okay, so when we're talking about number of particles, I can be talking about atoms, be talking about ions, right? Any kind of molecules, and so on. So the formula reads N is equal to NP over Na. Sometimes they just leave that as an N, right? So here it's moles, okay? This NP, there is no SI unit, but it must always be a whole number. And it can be in scientific notation. But if it's not you can't have 2.4 atoms. You can't have 1.6 electrons. That's what I'm trying to say. It's just not possible, right? For you to have that. And then Na over here is Avogadro's number at 6.022 times 10 to the power of 23. This is what we call a constant, and it is given on the formula sheet. Now, you were given formula sheets at the beginning of the year. Go and find this number on your chemistry formula sheet. That number will be given to you in exam. You just need to be able to identify the number so you can use it in the correct place. All right, so let me give you an example of how this works. Okay, so the first example they could give you, they could say calculate the number of atoms there are in a sample of aluminium that has a mass of 81 grams. All right, so let's just see what you have here. So they want number of atoms. So they want NP, which you don't have. They're giving you aluminium, so you know molar mass of aluminium that you get from your periodic table. So you go straight to your periodic table and you pull that up. Aluminium is 27. So that's 27 grams per mole. They've given you the mass at 81 grams. Now you need NP, okay? So what you want to do is you want to write down your formula with NP. N is equal to NP over Na. Now when I look at that formula, I need to just see if I have everything. Do I have number of moles? I don't have number of moles. So that becomes something that's in my unknown. I don't know that either. Do I know NP? I don't know that. Do I know Na? Yes, it's 6.022 times 10 to the power of 23. I know that, so that's fine. Now, I want you to note here, you cannot have two unknowns. Right? Now, we have a second formula. We have a second formula for N. We also know that N is equal to little m over big M. Okay? Now, I have mass and I have the molar mass, and I can use it to find that N. Then take that N and substitute it back in there. So it's a two-part calculation. I'm just going to go through it with you. So the first thing we need is number of moles. So we're going to say N is equal to little m over big M. Get a mark there. The mass here is 81 and the molar mass is 27. All right, put that into your calculator and you should get N is equal to 3 moles of aluminium. Okay, done, sorted. Now I need to take this value and put it into my second formula. So this is going to go N is equal to NP over NA. The N we've got is 3 is equal to NP, which we're looking for, over NA, which is 6.022 times 10 to the power of 23. And NP is then equal to, and you just pop the whole thing into your calculator, 3 times whatever the case is, right? And you should get 1.8066 times 10 to the power of 24 particles. Okay, now if I look at that number, we need to make sure we round off to 2 decimal places, right? So that's going to be NP is equal to 1.81 times 10 to the power of 24. And the particle we're looking for here is atoms in a sample of 81 grams of aluminium. And get used to writing these statements down. Write them down. So this is the full calculation. 1, 2. Let me show you mark allocations, how it would work for something like this. Okay, let me just show you the mark allocations. 1 for this formula, 1 for substituting, 1 for this formula, a substitution there, and 1 for your final answer. So 5 marks in total for a question like this. Please make sure that you're able to do something like this. Remember, everything that you're doing here is all the theory behind it. The real calculations are relatively more complicated, but you need to make sure you know how to sort out the basic calculations. Now let's do another little example. Right, example number 2. It says you have a sample that contains 5 moles of zinc. Okay. Question A, what is the mass of the zinc in the sample? And question B is, how many atoms of zinc are present in the sample? Okay. All right, so you got to do a little bit of analysis here. Please, when I do these examples, they're not here for show. They're not for you to just copy down. There are things that are going on here. All right, the first thing you need to sort out for question A is understand molar mass. Okay. When I look at zinc's molar mass, I know it has a molar mass of 65 grams per mole. Okay, that's its mass. That means that 1 mole of zinc has a mass of, remember the theory, mass of 65 grams. Okay. Now in this sample, they gave you 5 moles. So if 1 mole is 65, then 5 moles. So all we'll say there is 65 times 5, which is 325 grams. So therefore, the answer for question A, you would have put this calculation there, and your answer would have been 325 grams. So you'll need to do something like that. That is the answer for question A. You'd have to show us exactly what's going on in your thought process. Then question B says, how many atoms of zinc are present? Okay, so now you've got N is equal to 5 moles. That was given to you. And they're looking for NP, which you don't know. And they're looking for atoms. And you know Na, which is 6.022 times 10 to the power of 23. Info done. Right, so all you do is you say N is equal to NP over NA, and you've got 5 is equal to NP over 6.022 times 10 to the power of 23. So that's 5 times 6.22 times 10 to the power of 23 is equal to, NP is equal to 3.01 times 10 to the power of 24 atoms of zinc. And look how large that number is. That just shows you the size of one atom, how big one atom is. So when you do these calculations, you can see they're not just going to give you a simple sentence. Even though it looks simple, there are calculations that need to be done. The theory that I'm teaching you leads you to these calculations. By the time you come back in term 2, you need to know how to do these basic calculations, but I'm going to guide you through it. So it's not like I'm leaving you by yourself. Alright, this is the end of video 1. Once you're done with this video, you need to move on to video number 2, please.